coming to regioselectivity. Of even reaction. You know, regio means the direction. I can tell you that in all even reactions, ZZ, or you can say ZSEV, ZJF product is major product. ZZF product is obtained as a major product in all the even reactions. Let us take some examples. Consider this alkyl halide. Say this is 2-bromo-3-methyl butane. Yeah, as per the mechanism, in the first step, Br minus goes out. Okay, we get a carbocation. Then now see here the carbocation, whatever we got, the 2-degree one. As I said, a 2-degree carbocation, if at all, can be converted into a more stable one. If there is any possibility of this getting converted into a more stable one, just go for it. That is what I said. Rearrangements are always possible in even. So let me go for this. Now this is called 1,2. See, the hydrogen atom is moving from this to its adjacent carbon. Adjacent, so 1 and 2. If this is the first one, this is the second one. So now, see on 1,2 hydride shift, what do we get? CH3, then this becomes CH2. Here, the positive charge, then these. So now we got a 3-degree carbocation, which is of course more stable when compared to 2-degree. Okay, so finally we got a more stable carbocation. Now taking this more stable carbocation, Let us go for the second step and try to see what regioselectivity is and what a ZF product is. Now, CH3, CH2. Let me take it this way for convenience. We got a positive charge here, CH3. Even this also is CH3. And these two methyl groups, of course, are in the same environment. Let me consider this one for my explanation. This and this, both are in the same environment. And of course, both are beta. Beta. Even this also. So we have to take out a hydrogen from the beta carbon using a base, using a weaker base. That's what I'm planning now. Come on. And see, one. Now, there are two possibilities. Either this bond can come to the rescue of the positive charge, say possibility A or possibility 1, no problem. From this beta, the hydrogen may come to the rescue of the positive charge. And that hydrogen can, of course, be abstracted using a base. Let me take a base or this way. This way. Even here also. This way. This is possibility 2. Let this be the second possibility or possibility B. Now let me show you very clearly the products formed in these two cases. See, in case A, it will be CH3, CH2, then this, and now this is what is formed now, right? Okay. Then what is the product formed in the second possibility? Take B into consideration. Okay, if you want, I'll show it the same way as shown in the first one. Consider this. This is what is formed now. Now, we have to compare these two. Compare these two with the regular or the basic alkene, I mean ethene or ethylene. Okay, let us check of what has happened. See, in this you got two hydrogens. Check the number of hydrogens that have been replaced. Point number 1. then of course we'll go for the number of hyperconjugative structures. Now, see, this double bonded carbon has got both its hydrogens intact. That means both the hydrogens are still there as it is. No substitution at all. That means the double bonded carbon is unsubstituted. It has two hydrogens as it is. Whereas in this case, I mean, this double bonded carbon has actually got two substitutions. Right? One is methyl, the other one is ethyl. It has got two substituents. I mean, two hydrogens have been substituted. Coming to the second one. In this case, see, this double bonded carbon has two substitutions. Whereas this double bonded carbon has got just one hydrogen substituted and the other one is as it is. Anyways, in the first one, out of the four hydrogens what we had, two have been replaced. Two have been substituted. Whereas in the second one, I mean B, there are three substitutions. Right? Now coming to this, let me clearly tell you that this is a less substituted alkene. Only two hydrogens have been replaced. Lesser substituted alkene is of course less stable. It is because, you know, there are check out the number of hyperconjugable hydrogens. See, this has three hydrogens, whereas this alpha has two hydrogens. So there are five hyperconjugable hydrogens. Right? You know this a lesser substituted one which is a lesser stable because of five hyperconjugable hydrogens. And say this one which is a more substituted alkene, this of course is more stable. I can tell you that this is more stable because I can see 3 plus 3 onto this side and 3 onto this side. So a total of 9 hyperconjugable hydrogens are present in this. Greater the number of hyperconjugable hydrogens, greater is the stability. Right? And now, see, technically this lesser substituted alkene is called Hoffman product. And the more substituted one is called Sedzeff product. Check this out. Too many important points. And as I said, the more substituted alkene or the more stable alkene or the Sedgeff product is the major product here. So this is major and this of course is minor. That's it. Let us take one more interesting example. Say this. The first step is loss of halide ion, bromide ion in this case. We get a positive charge here. But the problem is, this is less stable. It is because of the angle strain that it has. If it can be converted into a more stable one, that means the one with the lesser angle strain when compared to this one. Yes, you can go for it. Come on. Let me go for this. See, now I'm going for ring expansion. Okay. Be little careful. Okay. See, earlier this bond was between these two carbons. Now this carbon has lost its bond, whereas this one is still holding the bond. It is the bond that it is holding. So let me just put a positive charge on this carbon because it has lost its bond, whereas this is still holding the bond. Now this can be written as this. A 5-membered ring, which of course is a more stable one. With a positive charge. See, this is a more stable one because of lesser angle strain. Now, the next step. Considering the hydrogens at the beta carbon. Beta, beta. All the 4 beta hydrogens are in the same environment. No change at all. And moreover, this secondary carbocation cannot be rearranged to a more stable one. We don't have any chance. But sometimes, even after ring expansion, we get a chance of rearranging it into a more stable carbocation. So ring expansion followed by shift is also possible. Now, take any of these hydrogens. Okay, let me just take this. Now this bond comes to the rescue of the positive charge. And finally, we get cyclopentene. This is how the alkenes are prepared. Okay. Let us now go for E2 reaction. E2 stands for elimination bimolecular. Just like E1 is elimination unimolecular, this is elimination bimolecular. Now coming to the mechanism of E2 reactions. These are one-step processes. It is also known as concerted mechanism. One step or concerted mechanism. Let me show you. Now this is an alkyl halide. Base abstracts the H plus, I mean hydrogen without the bonded pair. Of course, that is when we call it a base. Okay. A stronger base is what we use here, remember. As and when this happens, the bond comes here. At the same time, this also goes off. And say this step is the rate determining step or the slow step of the reaction. In fact, the only step. But in this step, we get a transition state. Let me show you what a transition state is. Now say this bond is going to get broken. Let me write B here. Bond breaking. This B minus is going to form a bond. Bond formation. There is a bond already present between the two carbons. Now a fresh bond is going to form. So this is BF. Now even this bond is going to go off. So this is again bond breaking. Okay. A transition state is the one where you have bonds that are going to form and bonds that are going to get broken. Partial negative, and even this also is partial negative. So we can actually put partial positive, two positive. So this is a transition state. Now, this is what we get. Check out. Along with this, of course, the base which has gone out along with the H plus, and of course, the X minus. Now, coming to the characteristics. The first one, see, in this case, a rate depends on the concentrations of both alkyl halide and the base. The first power of the concentration of alkyl halide and the first power of the concentration of the base. But how are these powers obtained? Keeping the concentration of the base as constant when concentration of alkyl halide is doubled, rate is also doubled. That is how we got this power 1. Okay. Now, second time, keeping the concentration of alkyl halide as constant, when concentration of the base is doubled, rate is also doubled. That is how this power 1 is obtained. So the powers are always determined by conducting experiments. Okay. So therefore, here the order with respect to alkyl halide is 1. Order with respect to base is also 1. Overall order of the reaction is a 2. Now when suppose the concentration of both alkyl halide and the base are doubled, rate is going to get quadrupled, isn't it? 2 power 1 into 2 power 1. Okay. So therefore, we can say that it follows second order kinetics. And see, as seen in the rate determining step, there are 2 molecules or say 2 species participating. Alkyl halide as well as the base. So therefore, this is bimolecular. See, from this it is very clear that rate depends even on the base, even from the previous discussion. Rate depends on the concentrations of both alkyl halide as well as the base. Let us see the effect of the base on the rate of the reaction. Rate depends on the concentration of the base also. In general, a stronger base is used. This is very important. Here I have two examples to discuss, just to make sure what a stronger base is and what a stronger nucleophile. In fact, a very good discussion can be taken once the substitution, I mean nucleophilic substitutions, are also discussed. We can actually compare the substitutions and eliminations. A very interesting discussion can be taken, but for now, let's see this. Check this out. You know, the first one is methyl alcohol, which is, of course, a weaker base. Once it loses a proton, we get methoxide. Methoxide, the second one, is a stronger base. See, in methoxide, there is a plus I effect of methyl group. As a result, electron density at the oxygen, which is already negatively charged, increases. More capable of donating its electron. So is the strong base. Now, generally we use the weaker bases for even reactions, whereas the stronger ones for E2 reaction. Okay, so this is how we can generalize saying the neutral one is generally are weaker. Anionic are generally the stronger ones. Okay. Now, one more thing. Consider this example. Methoxide this is tertiary butoxide. Plus I of methyl plus I of tertiary butyl. Looking at this, of course, we can simply say that methoxide is a weaker base, whereas tertiary butoxide is a stronger base, has got more electron density at its oxygen, right? So, methoxide is weaker, tertiary butoxide is stronger. But when the same thing is considered, is compared with respect to nucleophilicity, this is where the interesting part lies. Now, this can actually approach a carbon with a positive charge readily because this is a sterically less hindered. I mean, it's not that bulky, it's not that larger group, whereas this is bulkier, sterically more hindered, occupies more volume in space, bulky, larger, whatever, sterically crowded, more crowded. So, when this tries to approach a carbon with a positive charge, I mean, when it tries to act as a nucleophile, then that becomes difficult because of its bulkiness. So, approach of tertiary butoxide towards a carbon which is electron deficient is difficult. Therefore, we can say that it is a weaker nucleophile. Whereas the methoxide ion, which is not that sterically hindered, not that crowded, not that larger, not that bulkier, can easily approach the carbon with positive. I mean, the electron deficient carbon. So is so it actually approaches the carbon easily. Therefore, we can say that it is a stronger nucleophile. So this is very interesting.